Okay, now let's get going to the next topic that relates to, still relating to bonding of molecules, and see what the outcome of that. Again, structure leads to function, and we saw that atoms, and now we're going to see with molecules as well. Okay, so let me just give you a little heads up and how this video's how this PowerPoint's going to work out. It basically has three parts. First part's going to be going over shapes of molecules, and that'll be for the first 25 minutes. And then the second part will be including hybrid orbitals, which goes through about 55 minutes. And then the last part of this will go through the end of it, which is about 80 minutes. So there's three parts, each one about 26, 25, 26, 27 minutes. Okay, so first thing we'll do is look at molecular shapes. Okay, now, so we know that the bonding structure of a molecule, and the molecules tell us connectivity between the atoms and the molecules. Tells us number of bonds and lone pairs associated with each atoms. The structure is two-dimensional. It basically just shows it's connected, but it doesn't give us three-dimensional structure. When we draw the bonding structure, it's easy to think that we drew it like flat surface. Might actually represent it. For instance, methane. When I draw methane, it looks like a cross. And you may think it looks like this in 3 dimensions, but it doesn't. It doesn't look like that at all. Right. Like I said, all it does is show connectivity. So we could write. So when we write out water, we might write it out like this when we figure out its bonding. But we could also write it like this, and we could also write it like this. I mean, it doesn't matter. The main thing is that you see that it has two bonds. Between the oxygen and hydrogen, and it has two lone pairs. Okay, you know, it's nice to draw it symmetrical, but it doesn't have to be, okay? At least when you're doing two dimensions. Now, what we'd like to do is when we do write it two-dimensionally on a piece of board, we do actually like to draw it in a way that kind of would represent it as 3 dimensions as well. Well, it's hard, and you kind of just have to visualize it. Okay, so what we want to do is find a 3-dimensional structure of covalent molecules. And what we're going to do is start out with beryllium dihydride. So let's find out its bonding structure. It has each beryllium has 2 valence electrons, and each hydrogen has 1. So number of 4 valence electrons. So the skeletal structure is this right here. Okay, the way that we've been doing it, we say give the outer atom its number of bonds. Okay, hydrogen always gets 1 bond. Okay, then you count up the number of dots, which there's 2 dots per dash. And then you, so there's 4 dots. And if the number of dots equals the number of valence electrons, you have the right structure. Okay. So this is the bonding structure for BeH2. Okay. So what we want to do is see what this guy, what does this guy look like in 3 dimensions? All right. First, around each atom, we know there are electrons. Okay. So there's valence electrons around hydrogen, beryllium, and hydrogen. So electrons have negative electrical charges, and they repel each other. So the electrons of this hydrogen here are naturally pushing against this beryllium, and this pushing against this one and this one. All right. Okay. Now, what we're going to do is also, so we have this initial structure, but what we're also going to do here is, so we have to think about this three-dimensionally, and what we're going to do is allow a pivot point around the atoms. And what we're going to do is allow the atoms to swivel any way they want. Okay, as long as they stay attached on a straight line. All right, now you can imagine that if this hydrogen somehow swivels, it gets really close to this hydrogen, what it's going to do is it's going to be repelled and be pushed back. Okay. And there's constantly that's going on. And actually you have to think about molecules. Atoms are not stationary on molecules. They can move around. But what they do is they usually find the most stable position that they can be in most time, and that's going to be as far away from each other as. Okay, so here's a diagram of that. So this hydrogen might get here, and then what it'll do is swing back. Okay, because there's this, and so you get this bouncing back and forth. Okay, then eventually what happens is the hydrogens want to be away from each other and the beryllium as far as they can. And what they do is they just have, they are 180 degrees apart from each other. Okay. And now this would be a straight on view. Okay. So, but there's also another view from this you could take a look at. So if you look at, so here's my eyeball here, and if you look at it from this view, you'll see that it looks like this. Okay, and then maybe if you looked at it from the side, it may look like this. So the key thing here is it's straight across one dimension, and it has and then its point in another direction. All right. But the main thing is it's not a straight line, all right? It's a line, but it's not a two-dimensional line. It's a three-dimensional line that can be turned on its ends. Okay, so we usually draw it like this, and in a straight across fashion. Okay. Key thing to realize is we really can't draw what it looks like on a flat surface. It's hard to do, but it's hard to do it in 2 dimensions. But you have to get the idea, all right? So one way is kind of think about it in terms of an angle like that. But anyways, we usually draw it like this. Now this molecule, the shape is called linear. And here's one of the key things about linear molecules. If the center atom has 2 atoms attached, beryllium, the center atom, it has 2 hydrogens attached, and there's no lone pairs on the beryllium, the shape will be linear. And what that means is everything is 180 degrees apart from each other. They're the outer atoms. So this is the key thing right here. This is one way to determine. So if you can't see it, so if you can't see actually see the three-dimensional, you can just look at the connectivity and you can tell what the three-dimensional shape is. So knowing this information here, you know it's three-dimensional shape. Right. Now let's do another example. Let's use beryllium trihydride. Okay, find the bonding structure. So boron trihydride. Boron has 3 valence electrons. It's in column 3. Hydrogen has 1, so there has to be 6 valence electrons. Skeletal structure. Give hydrogen its number of bonds, 1, 1, 1, and 1. Number of dots, 2, 4, 6. So this is the right structure. So what does this structure look like in 3 dimensions? Well, the way that I drew it, it kind of looks like, I don't know, a line with a hat on top of it, okay? But is that so? Let's take a closer look at what it looks like. Okay, again, what we're going to do is we're going to allow the hydrogens to swivel around on the bonds, okay, and move. So here's an example. Now this hydrogen starts to move too close to this hydrogen. What happens is it repels, and then it bounces back. And then you might get this guy swinging around and trying to get close to this hydrogen, and what does it do? Bounce back. All right. When it all is said and done, this is the shape that we get, at least from one view. It kind of looks like a triangle. Okay, now we'll see in a second. This is this one view. Okay, this is a two-dimensional view, but we have two other views to take a look at this as well. All right, so here's the view I just had. But if we look at it from the side, you can kind of see that it forms a straight line, or more realistically, it forms a plane, because a plane can be drawn, can go through this this view here. All right. So what we're going to do is name it according to its triangle shape and the fact that you can put a plane through it. So this shape here is called Trigonal Planar. Okay, now by looking at, just like we did in the previous example, by knowing the center atom and what atoms and lone pairs are attached to it, we can determine its shape. So if I just draw this out, you can determine what its three-dimensional shape is. So if the center atom has three connections, and we're going to make clear that those connections can be a bond, a single bond, a double bond, etc. And the center atom has no lone pairs, then it will be trigonal planar. And we're going to put this all together in a table in a little bit. Okay, now let's go to four connections. All right. Methane, we did that before on a previous PowerPoint. It has this bonding structure. Again, we're going to allow the hydrogens to swivel around. Okay. And what happens in this case is it doesn't form this cross shape. In fact, it forms a shape that's really hard to draw in 3 dimensions. It kind of forms like a tripod, like this, with an H attached to the tripod. All right. So you have so it has, whoops, let me do it again. So you have your tripod, right, with carbon here, hydrogen here, and there's another hydrogen coming off the top. You can see that's really hard to draw in 3 dimensions. And this shape here doesn't do it justice at all, okay? So it'd be really good if I could show this to you in 3 dimensions, but the best way to kind of do it is think about it as a tripod with a piece that's coming off the top. All right, this shape is called tetrahedral because if you connect all the atoms together, they will form a geometrical shape called a tetrahedron. Okay, and again, we can tell what the shape is by knowing the connectivity of it. So if you have a center atom that has 4 things attached, 4 connections attached, and no lone pairs, it's tetrahedral. All right, next one. Let's take a look at ammonia. So ammonia, we can draw it out like this. We did this in a previous PowerPoint. Okay, and now what? We're going to let everything swivel. Okay, all right. Now, so what you're going to get in this case is these hydrogens are going to move And they can move this way, but now not only can they bump into the hydrogen, but they can bump into this lone pair. So this hydrogen sees this lone pair, it's going to bounce back, and so forth. All right, so this lone pair sort of acts like another atom when everything starts bouncing around. So it kind of looks trigonal planar, just like we had before. Right, and it forms this triangle shape. Okay. But the thing here is the lone pairs. Okay, the lone pairs are going to cause this not to be a linear planar shape anymore. Okay, so trigonal planar was all the atoms were in the same plane. For this guy, they're not. So what we're going to get here is the hydrogens are going to be in one plane, and the nitrogen are going to be up here with its lone pairs. And that's because the lone pairs push these hydrogens down. Okay. So from one view, it's trigonal, but from the other view, it's not planar anymore. It's no longer a straight line or a plane. Okay. All right. So what we have is it kind of forms a tripod. It forms this tripod again. Okay. But instead of having an atom up here, it has a lone pair. Those lone pairs push these hydrogens from being planar. Okay. So this shape is going to be trigonal like previous one. Okay, so it's trigonal, but it's not planar anymore. Okay, because all these atoms are on a different plane than this one, and this shape here looks like a pyramid. All right. So we call it Trigonal Pyramidal. Okay, now one way to tell if you have a Trigonal Pyramidal is if the center atom has 3 connections, 2, 3, and a lone pair, then it will be Trigonal Pyramidal. That should be I here. All right, now we're going to go to water. Water looks like this. We figured that out before. Now they can swivel around, and they keep on hitting each other, and sooner or later what the shape is going to be is the shape is going to kind of look like this when you get done from one view. Okay, from another view it will look like this. Well, it's like this up here. And if you turn it on its side, it's going to look like this. So three-dimensionally, it's hard to draw this. I mean, actually see it. So you have, here's your connectivity, and then you have your lone pairs. You don't need to have, these are not really bonds, but they're just show how they're connected. So you can see, just like this forms the same kind of shape as Trigonal Pyramidal and Tetrahedral, but 2 of the bonds are replaced by lone pairs. Okay, so this is not a straight across molecule like in beryllium dihydride. The lone pairs will cause it to form a bent in that line. And so we call that shape bent. So a bent molecule will have 2 connections and 2 lone pairs. Sometimes just 1. Okay, so let's put it together, okay, in terms of the connections and lone pairs and the shapes. So we said when you had two connections, two lone pairs to the center atom, it's got to be the center atom, the shape will be linear. If it has three connections to the center atom, has three connections, and no lone pairs, is trigonal planar. If it has four connections and no lone pairs, it's tetrahedral. If it has three connections and one lone pair, okay, it's going to be trigonal, just like up here. But now it's going to be pyramidal, okay, and that's from its side view, it's going to look like that. And if it has two bonds and two lone pairs or one lone pair, it's going to be bent, okay. So this is one view. From another view would be straight on, okay. But it's hard to draw that. So these three here are hard to draw in 2 dimensions. Now, a clarification about this word connection. All right, this word connection, this tells me the connectivity between atoms. So, for instance, this carbon here has two connections to it and no lone pairs. So this would be linear. It has two connections, two lone pairs. So the connections can be more than just one. All right. Now, okay. So in a previous PowerPoint, we talked about sigma and pi bonding, and what we want to do is relate that to, and we related that to the different kinds of arrangements of bonds. So, for instance, carbon has 4 single bonds, and because they're single bonds are always sigma bonds. So carbon, if you have a carbon with 4 single bonds, it has 4 sigma bonds. Right? That means all of them are going to form sigma bonds. That's right. Now, if you have a carbon with, well, let's start out with this one. No, let's start here. Is that if you have a carbon has 3 connections, that means, so remember, there's 4 different ways that carbon can have bonds. It could have 4 single bonds. You can have 2 single bonds and a double bond, 2 double bonds, and 1 single and 1 triple. Okay, in this case here, it has each single bond is sigma, and one of the bonds in the double bond is a sigma, and the other one is pi. Okay, so that's a carbon with 3 connections. So a carbon with 2 connections, okay, like this, it has 2 double bonds. One of the bonds is sigma, the other one is a pi bond. And then finally, you have another 2 connection. We have a single bond, that's just sigma, and you have a triple bond where one of them is sigma and the other 2 are pi. Okay, what we want to do is show that how this relates, why this is. Okay, at this point, you may want to take a break because we're going to start something. We're going to continue what we're obviously, but the next part is going to be sort of added a new addition to it. Okay, all right. Okay, so here's the overall energy diagram for the Lewis dot structure for carbon. So so carbon has 6 valence electrons. 6 electrons and 4 valence electrons. So it has 2 in the S and 2 unpaired in the P. Okay, in the Lewis structure, you notice that it has 4. So what we want to just do is look at the valence shell. And this particular, when we look at the OED, there are 2 unpaired electrons, 1 paired and 1 unbonding, okay, or non-bonding orbital. But when we look at the Lewis dot structure, it has 4 unpaired electrons, and these are not equal. All right. This here says that there should be basically 1 electron in there should be 4 unpaired electrons in the second level. Okay, but that's not what predicted in the orbital energy diagram. Okay, we know this is true. We know that carbon has 4 bonds, but the orbital energy diagram doesn't work. But the orbital energy diagram works for the individual atom, but it doesn't seem to work for the way it bonds. All right. Okay, so what we want to do is to try to describe what's going on here. So we're going to just look at energy level 2. All right, so energy level 2. So energy level 2 has an S subshell and a P subshell, and an S subshell has a lower energy than P. So really, I really showed that separation here, and this is higher energy than this down here. This is the shape of the orbital, and these are the shapes of the 3 orbitals in the P. So there's 2 guys in here, and there's 2 electrons. We'll just put them in here and here. Doesn't matter so much. Okay. Well, this is our starting point. So this is the OED model. Okay. For the set. Okay. Now one of the things we can think can happen is that this p orbital and s orbital somehow come together and they form hybrids. They're part S and part P. And so what we're going to do is use this idea of forming hybrids to help explain how carbon can form those 4 different arrangements. Okay, so we have, so this is our OED. Okay, so there should be another orbital over here. And there's 2 electrons. Okay, so now what we think, and it seems to work, and by the way, this is called a theory, a hybrid theory, is that the s orbital partially combines with one of the p's. So one of these p's, let's say this guy right here, and is going to mix with this guy, and it's going to form a hybrid. Okay, that's part S and part P. So it's going to be half P and half S. So it's going to have a higher energy than S, but a lower energy than P. And it's going to be, if you draw it, it's going to look like it's half S and half P in its in terms of its shape. Okay. So overall, if you have carbon in this situation, it can have 2 P's electrons, and it can have 2 sp electrons. We'll see how that ties together in a little bit. Okay, so now there are 4 unpaired electrons. All right, there's 2 sps and 2 p's. All right. Right, 2 double bonds. So what we want to do is see how it relates to this situation here. We have where you have a 2 double bond carbon, double bond carbons. And so the p's are always going to form pi bonds, right? So these two p bonds are going to form pi's. So that this sp hybrid, where we'll have two pi bonds that form from the p's. Okay, and then we'll have two sigma bonds that form from the SPs. Okay, and that's what we have right here. Is that when carbon double bonds, you have two pi bonds. Okay, we said that one of the bonds is sigma, one is pi. So here's two pi bonds, and it has two sigma bonds. So if you see a double bonded carbon with two double bonds, is going to have sp hybrid orbitals as well as two p's. Right, another way it can form is that we saw before, is that if you have a carbon that has one bond and one triple bond, okay, the single bond, these two guys are pi bonds, right? And they come from this up here. And the other two sigma bonds come from the SPs. Okay. So anytime you have, if you have a two connectivity carbon, either there's two double bonds and one triple bond, one single bond, the hybrids are going to be SPs, and they're going to form sigma bonds. Okay, the next possible hybrid, okay, is where now two of the P's are going to combine with S. All right, and when they do that, you get this new hybrid, which is, so it's made out of three different orbitals. So each one of these orbitals in the subshell is going to be part S and part P. So it's going to be each orbital is going to be 1/3 S and 2/3 P's in its shape. Now in this case, these guys are going to form three sigma bonds, and then you're going to have a pi bond as well. So what connectivity arrangement for carbon has three sigma bonds and one pi bond? Okay, it's this arrangement down here. Okay, so these two sigma bonds are an sp2. This is also a sp2, and then it has another p that's going to form a pi bond. Okay, so when you have this arrangement, it's going to have an sp2 hybrid. Okay, so these are 33% S and 66% P. Okay, finally is the three P's connect with the S to form four hybrid orbitals, which we call sp3. That's because they are essentially made out of 1/3 S, 1/4 S, and 3/4 P. Okay, so they look more like P's, and their energy is quite close to P, and they're all identical energies. Okay, so now each one of these will form a sigma bond. Okay, and what arrangement a carbon will have four equal bonds? This guy right here. So whenever you have this carbon right here with four single bonds, sigma bonds, it's going to be a sp3. So let's just put this together, what it all looks like. So this is your orbital energy diagram. that we start out with. There should be another one over here. Okay, then our first type was SP, where the S combines with one of the P's and it forms SP hybrid. So in this case, we'll form 2 sigmas and 2 pi's. And here's the case where you have that. Okay, there's 2 sigmas and there's 2 pi's. There's 2 sigmas and 2 pi's. So whenever you have double bonded carbon and triple bond carbon, the hybrids will be SP. The other guys are, and they'll form sigmas, and the other bond will be a pi bond from a P. Okay, now the other type is where 2 of these combine with S, and it forms an sp2 hybrid. Now notice it's a little bit higher energy than this guy. That's because it's got more P-like, because P has a higher energy than S. And its orbitals also starts to look more like P. This can form 3 sigmas from the sp2 hybrids and 1 pi bond. And this is that case, okay? 1 sigma, 2 sigma, 3 sigmas, and this guy's a pi. Each one of these sigmas is from sp2. Okay, and okay, here we go for the fourth one, is where you have 3 P's forming a hybrid with the S. You get 4 of them, all equal. Their energy is close to a P. You can put 4. They can have 4 bonding, each one forming a single bond and a sigma. So if you have 4 single bonds, it's a sigma. I mean a sp3 hybrid. Now, we're just basically giving introduction to this. If you go into organic chemistry, you will be getting this again and in a lot more detail. All right, so let's put together some of the things we've seen here. Okay, so first of all, let's look at well, we came up with the shapes. Okay, so here's the different. Here's a diagram. Here's the table I had before. And here's number of attachments, and number of attachments are what's attached to the center atom. Okay, and that includes lone pairs. Okay, and we'll get into this a little later. So kind of you don't have to worry about this right now. Just focus on this and this over here. Okay. So what we just noticed is that. So let's look at carbon dioxide. Carbon dioxide has 2 connections, no lone pairs, so it's linear. So what we just saw is that whenever you have a carbon with 2 double bonds, or a carbon with a triple bond and a single bond, it's going to be an sp hybrid orbital that forms the sigma bonds. Okay, that's going to be the general case. The general case is whenever you have a linear molecule, the hybrid it will form will be a sp. Okay, so that's pretty cool. So what this does is if you know the shape, you can figure out the hybrid orbital. Okay, so let's take a look at this carbon here. And this doesn't even have to be carbon. So the previous example where we had beryllium dihydride, and we said that this was a linear molecule. Okay, these bonds are SPs. Okay, so it doesn't matter that it's carbon, right? So let's take another example. Okay, and we went over this one. This guy's called formaldehyde. So this carbon has 3 connections, okay? And it has, and we saw that when you have a carbon with this situation, okay, 2 double bond, 2 single bonds and a double bond, it formed sp2. Well, this shape is trigonal linear planar. This is sp2. Therefore, it turns out, whenever you have a trigonal planar molecule, the hybrids are sp2. So if we went back and looked at boron trihydride, and we ask what kind of hybrid that has, it'd be an sp2. Okay, we saw for this arrangement is that you have 4 connections, and that's where you have the sp3s. Okay, all right, now let's go to the 2 other shapes we had. Okay, now we're going to use the attachments. Okay, so really the key thing here is what's attached to the center atom. All right, so this carbon had 2 attachments. This had 3. This had 4 attachments, and this had 4. This had 4 attachments, and turns out this has 4. Okay, so really the key thing here is the number of attachments. And so if the center atom has 2 attachments, it could be either lone pairs or bonds. It's going to be sp. Okay, if you have 3 connections, and they can be lone pairs or bonds, then it's going to be sp2. For instance, I don't know, if you had a molecule that looked like this. Or it has 2 bonds, 1 lone pair, that's going to have an sp2 hybrid. Okay, so this case, this has 4 connections, and they could be all lone pairs, or they could be lone pairs or bonds, and we'll see in a second. Yeah, hybrid's going to be sp3. So if we look at ammonia, it has 1, 2, 3, 4 attachments, where 1 attachment's a lone pair. That's going to notice it. Its shape looks a lot like the tetrahedral. The hybrid is sp3. And water has 4 attachments, 2 bonds, 2 lone pairs. The hybrid is sp3. So if we look at the center atom, we can figure out its how many things attached to it. We can figure out its hybrid orbital. Now let's look at the kinds of molecules the hybrids will form. sp hybrid bonding yields 2 attachments. Okay, sp2 will have 3 attachments, and they could be single bonds, double. They could be bonds or lone pairs. sp3 will have 4 attachments, and they could be single bonds or lone pairs. And each of these hybrids have a particular shape. And sp has linear, sp2 has trigonal, and so forth. Okay, let me explain that. All right, so now we can extend this, and so here I have a table, and what I have here is my attachments. Okay, and this can be just some random molecule. So here's 2 attachments, here's 3 attachments, 4 attachments, 5 attachments, and 6 attachments. So in the first case, if you just have a molecule with center atom that has two attachments, and we're just going to assume they're two bonds, that means there's no lone pairs. The hybrid is going to be sp. Okay, now if you have a molecule with three attachments, it actually could have three bonds, like this, or it could have two bonds and one lone pair. Okay, so here's three bonds, no lone pairs, two bonds and one lone pair. That is going to be sp2. Both are sp2. Right. If you have four connections, you can have, like in CH4, four bonds and no lone pairs. You can have, like in ammonia, three bonds and one lone pair. And then, like water, two bonds and two lone pairs. All three of those are sp3s. Okay, now it turns out we can have more, and we'll go into this in a while. Let's say you have five attachments to a center atom. Well, you can have five bonds, no lone pairs, four bonds and one lone pair, three bonds and two lone pairs, two bonds and three lone pairs, and they all have what we call an sp3d hybrid. Okay, so now what happens is that the hybrid actually expands into the D subshell. Okay, and then if you have six attachments, you can have six bonds, no lone pairs, and so forth. And these would be sp3 D2, okay, or D2 sp3. Now, if you take a look at these, this is made out of two orbitals, two hybrids. Okay, so it has two hybrids, one sp and two sps. This guy here, so if it's a sp2, it will have three sp2 orbitals. Okay, so there's three. So if you look at each one of these, this is sp, this is sp, and this is sp. All right. sp2. And if it's linear, okay, this bond is going to be sp and this can be sp. If you have sp3, like in terms of tetrahedral, sp3, 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 and sp3. The way I kind of think of it is it's one s and three p's. So combined together in one orbital. So s plus 3 is 4. So 4 connections. 4 attachments. These have 1, 2, 3, 4, 5 connections. 3. Okay, so that's kind of a way to remember it here. So an sp3, so if you look down here, sp3 means that it's 1 part s, 3 parts p, and 1 part d. All right, so let's look at a couple examples of these expanded type of orbitals in octets. Okay, so we have PCl5, and we went over this in previous. It has 5 attachments. Okay, all of them are bonds. Okay, so go back to the previous table and find which. So look at the one with 5 attachments, and you'll see that's sp3d. So each one of these is a hybrid of sp3d. Now, if you look back at the table as well, you see the one that has all of the attachments are bonds What is the shape associated with that? It's called Trigonal Bipyramidal. Okay. Now, if it had, instead of having five bonds, and it would have four, and a lone pair, it would have a different shape, but the same type of orbital, hybrid orbital. And you won't have to memorize that table, you just have to know how to use it. Okay, so let's take a look at ClF3. Okay, so first of all, let's find a bonding structure. Number of valent electrons is 28. Okay, 7 plus 3 times 7 is 28. Here's the skeletal structure. Now let's put fluorine gets 1 bond and 3 lone pairs. So we do that and we count the number of dots. We have 24. We're missing 4, so we put 2 in the middle, 2 pair in the middle. All right, now we can see this molecule has 5 attachments. Okay, it has 3 bonds and 2 lone pairs. So what's the hybrid associated with that? sp3d. And then if you look at that, look up that shape, where it has 3 bonds and 2 lone pairs, it's what we call T-shaped. Okay, let's do another one here. Bromine Penta Fluoride. Figure on valence electrons, draw the skeletal structure, kind of make it symmetrical. Fluorine gets the outer atom is fluorine to give its number of lone pairs. And bonds has 1 bond and 3 lone pairs. Count up the number of dots. So it's 2, 4, 6, 8, 10. There's 5. Okay, so there's 40 altogether. Each dash it's 2. So we're missing 2, so we put 2 in the middle. Okay, so this molecule has 6 attachments. Okay, 5 bonds and 1 lone pair. So that hybrid is going to be sp3d2. Okay, so 1, 2, 3, 4, 5, 6. Okay, if you go look up the shape, it's called square pyramidal. Okay. And that shape is going to kind of look like, I believe, like this. So we have 1, 2, whoops, there, let's do this. So, it doesn't matter, but so it's going to call it square pyramidal, and so you have 4 of the fluorines in the corner of a square. Okay. The bromine is right in the middle. There's a lone pair at the bottom, and then there's another fluorine at the top. Okay. All right. And if you go back and look at the table, you can kind of see that as well. Okay, just like in the last one, at minute 25 or so, I had finished part. So we just finished about hybrids here. What we're going to do is we're going to get into polarity next. So if you want to just take a little break here and go forward. Okay, next thing we're going to talk about is polarity. Okay, now one of the key things, so what we have here, what we learned is that structure leads to function. We saw that with atoms. Structure of an atom determines the electronegativity, how well it gains and loses electrons, and so forth. And we can also apply this to molecules. And molecules, the shape of a molecule is going to determine its function. Well, it has to do with its chemistry, but also what we call polarity. So polarity is going to be actually a function based on the structure of an atom, a molecule. So what we're going to do is just take a look at hydrogen molecule H2. And we know the bonding is in this right here. Now what we're going to do is that these guys aren't just blocks of wood with no personality. Their personality is basically their electronegativity. How well they gain and lose electrons, or hold on to, or help basically hang on to the electrons. And we learned that electronegativity is dependent on size, and smaller atoms have higher electronegativities. And we learned that if you had the periodic table, the elements up here have higher electronegativity than those down here. Okay. All right. So we know, so we can say, in the case of covalent bonds, each atom shares a shared pair and is pulling on that shared pair with some force. And that force is related to its electronegativity. Okay, now hydrogen, that force is given the value of 2.1. Now how do we know that number? Well, it's a number that's kind of based on empirical data. It doesn't have a unit. It's this base. It's sort of, it's qualitative, quantitative values sort of. So if we take a look at hydrogen, this molecule is straight across. It's kind of linear. Where this hydrogen, so you have this lone pair here, and what you have is this hydrogen's pulling on it with a strength of 2.1, and this one is also 2.1. In that case, these electrons, it's like a tug of war, and these electrons are going to stay, going to be pulled this way and pulled this way, and then they'll end up staying exactly where they are. They cancel each other out. Now, this can be kind of related to vectors. Okay, a vector has magnitude and direction. So this has a magnitude to the left, with a direction to the left, 2.1, magnitude of 2.1. This has a magnitude of 2.1 to the right, and okay, so here's the table of electronegativity. These are values that are qualitative, quantitative, originally developed by Linus Pauling, and this must be European because there's commas instead of decimals. Okay, so in the next few slides I'll be using this. Okay, so now let's take a look at another molecule. So what we can do is replace one of the hydrogens with a fluorine. In this case, fluorine has a electronegativity of 4.0, and you can there are periodic tables that have these numbers in that you can look up. Okay, so you have fluorine pulling on it with 4.0 this right direction, 2.1 to the left. Again, this is a linear molecule, so it's like it's tug of war. In this case, the tug of war is going to be basically won by the fluorine. Okay, when you add these two together, so if you add vectors, so it's going to be basically 4.0 plus, if you do it right to left, plus negative 2.1 going to the left. The overall is going to be, let's see, call that plus, going right. And then, so it's going to have a net of 1.9 to the right. Okay, that means this lone pair here is unequally shared, and most of it is being pulled towards the fluorine. So if you were to kind of draw it, it'd be, the hydrogen's going to be like this, and the fluorine's going to be like this in terms of electrons. Okay. So in the end, the shared pair is not equally shared anymore. Fluorine has more of the pool, and thus becomes more negative. Okay, so because it has more than negative. And where they get the negative from, it got the hydrogen, so the hydrogen became less negative that means it became a little bit more positive. So what we can do is kind of write it like this, where it becomes partially positive. The hydrogen becomes partially positive. This is a little delta, and it becomes partially negative, the fluorine. So this partial positive charge, partial negative charge. Another way you can demonstrate that is by drawing this arrow, showing that this is the positive part, and that the electrons are being drawn towards the fluorine. Okay, and that's described here. Another way you kind of can draw it is kind of like a magnet, but it's not magnetic. These are electrical. It has a negative pole and a positive electrical pole. So this side is the negative electric side, and this is positive electrical side. Now, because of this, it has a pole. It has a positive pole and a negative pole. So we call this molecule a polar molecule. Any molecule that has an unequal sharing of electron is called a polar molecule. Okay, while molecules like H2 have equal sharing are called nonpolar molecules. Okay, now we'll get into this at some point up here. Is that there's a difference between there's things called polar molecules and polar bonds. This is a polar bond and also a polar molecule. Okay, so now let's take a look at this molecule here, beryllium dihydride. We already looked at this one, figured out its shape. It's linear, has two connections and no lone pairs. Okay, and also it's sp hybrid. Okay, now let's take a look at it in terms of electronegativity. Right, so we have beryllium with 1.6 and each hydrogen with the 2.1. And let's take a look at the individual bonds first, okay? So this bond here, okay, so it's 2.1 being pulled to the right, to the left, and 1.6 to the right by beryllium, so there's a net of 0.5 to the left, okay? Now, the other direction, the beryllium's going to be pulling on these guys equally, so it doesn't like split half of it. So going in the other direction, it's also 0.5. All right, and if you want, you can call this plus 5 and this minus 5. All right. Okay, so each one of these bonds is what we call a polar bond, because one side is positive. So in this case, this side would be positive, and this side negative. All right. Now, when you put these two guys together, you'll notice is that the two polar bonds cancel each other out, and that's because of the linear shape and the equal and opposite atoms being pulled on it. So this is a nonpolar molecule that has polar bonds. Okay, now let's do beryllium substitute with the fluorine. Okay, so again, if we look at the individual bonds, this is negative 0.5, and we'll say it's going this direction to the left, and going this way is 2.4, 4 minus 1.6 plus 4. Okay, so both of these are polar bonds. Okay, and in this case is that the fluorine is going to outweigh the hydrogen, and overall the molecule is going to be, electrons going to be pulled towards the right by the difference between these two, which is 1.9. And so this molecule is a polar molecule. Okay, that's because of the fluorine. So both of these have the same shape, but what determines it, the polarity, is not the shape. but the type of molecule, the atoms that are attached to the shape. So if you have same shape, different atoms, you can have different polarities. So what you get is this case right here. So this is a polar molecule, and the BeH2 was not polar molecule. So you can kind of draw it like this: partial charges. So this is what we call polarity. So polarity is when the overall charge distribution, the polarity is the overall charge distribution of shared electrons in a covalent molecule. That's what polarity is. It looks at the overall charge distribution of the electrons. A polar molecule is when they're unequally shared. Nonpolar is when they're equally shared. So one way to affect polarity is if you have the same shape, you can change the atoms to get different polarity. Okay, so let's look at water. In this case, I'm going to assume each bond is polar because they're each pulling. And what I'm going to do is just look at the hydrogen and how they affect each other. So the way that I have it drawn out here, it looks like the two hydrogens are going to cancel each other out, just like they did in the BE example. Okay, we found out that this was a nonpolar molecule because each one is tugging against each other. So this oxygen here is basically being pulled in equal opposite directions, and the electrons are staying put. It looks like the hydrogens are canceling each other out. Okay, but now what we have to do is that we have to be careful about it, all right? Because the key thing here is that this was a linear molecule, while this isn't. Okay, I draw it like it's linear, but if you go back and look, water actually can look like this if you turn it on its side. Okay, so this is one view and this one view. Okay, it's bent, so we have to take into account. Okay, so here I drew it in its bent shape. Now if you look at it, you can see that electrons are being pulled this way and they're being pulled this way. Now in terms of vectors, okay, if you've ever learned about it, this guy here has two components. It has a vertical component and a horizontal component, all right? Okay, so here's the vertical component and here's the vertical. Okay, now it turns out that the two horizontal components will cancel out because they're going in equal opposite direction, but the two verticals add up, tail to tail, okay, head to tail, and therefore this molecule overall has an unequal distribution of electrons. Okay, so in the previous example with beryllium dihydride, okay, the vectors didn't have a vertical component, they just had two horizontal components. Okay, in this case they have both, and then you get this. Okay, so what happens is that the molecule will have unequal distribution of electrons. Now I kind of cheated a little bit here in how the electrons, I said the electrons are being pulled towards hydrogen, they're actually being pulled towards oxygen, but I just want to get this case across. All right, the electrons are always pulled towards a more electronegative atom, and usually the atom has lone pairs. Okay, so overall it's going to have this case here where the oxygen is going to be more negative than the hydrogens. So water can kind of be drawn like this, has a positive part by the hydrogens and a negative part by the oxygen. So it's a polar molecule. And the reason why it's polar is not because of the atoms that are attached, it's because of the shape. Okay, I didn't have to change the atom here to change the polarity. I just changed the shape. So you can have two molecules that have the same atoms attached at different shapes, and you can have different polarities. Okay, so put this together. So the determination of the polarity of a molecule is it's determined by two things: the electronegativity of the atoms attached and or the shape of the molecule. So the first example we had BeH2 and BeHF. Okay, they have the same shape. They have different polarities because of the different atoms attached. And so the electronegativity of fluorine changes the polarity. All right, now in terms of shape, this can also change polarity. For instance, again, you had this molecule has two hydrogens attached. It's linear. And then we had water that had the same atoms attached to the center atom, hydrogens, but it's polar, and the reason why it's polar is because of the shape, bent. Okay, so we have to take these two things in account. Now what we want to do is, I mean, this is, as far as your class 121, you guys should be able to try to figure out if a molecule is polar or non-polar by going through all this. But what we're going to do next is try to come up with a fast way to determine polarity. Okay. In chemistry, there's lots of shortcuts. Okay, I often call them quick and dirty tricks. We learned at the beginning of the year that all elements in the first column have a +1 charge. Column 2 has +2 charge, and so forth. And then finally, over the last couple weeks, we learned out why. We also used the crisscross method to figure out the subscript in ionic compounds. Another shortcut. We could figure out the valence, number of valent electrons in valence shell by knowing what row column it's in, and how many energy levels by knowing what row it's in. And also we can look at, if I know electronegativity, atoms in the top right of the table have a higher electronegativity than the atoms that have in the lower left. So there's patterns that we use as shortcuts, quick and dirties, to help us get to where we are. And that's what we're going to do now, is we're going to come up with quick and dirty tricks, figure if we have polar or non-polar molecules. Okay, two tricks that identify polarity. And again, it doesn't explain why it happens. They're sort of tricks. All right. Again, what I just told you, the Y's are electronegativity of the atoms attached and the shape of the molecule. So what are the tricks? Okay, trick 1. Given the bonding structure, if the center atom, and right now we're just going to deal with atoms that have a center atom and things attached to it. We're not going to deal with atoms that are more complicated, like this. Okay, we're only going to deal with molecules that have a center atom and they have atoms that are lone pairs attached. Given the bond structure, if the center atom has more than one thing attached, okay, and what does that thing mean? Here's the key word. It's just like we did with figuring out the sp2s and sp3s, okay? The thing could be either lone pair or a bond. If it does that, if it has more than one thing, different things, the molecule is going to be polar. The other is opposite true. If their center atom has the same things attached to it, it will be nonpolar. So let's look at that, see if it works. Okay, we saw that BeH2 and BeHF. BeHF has two different elements attached. It has an H and an F. And we saw that it's polar, okay? So it has two different things attached, two different types of atoms. It's polar, and it was polar. So this so far is true. Okay, BeH2 had just the two hydrogens attached, all right? and we said it was polar. So again, it has the same things attached, and it's nonpolar. Now, how about water? Okay. Now, if you just look at water, it looks like the oxygen has the same things attached to hydrogen, but you have to draw it out. And you see now it has two different types of things. It has bonds, hydrogen bonds to hydrogen, and lone pairs. So it has two different types of things. So we said if it has two different types of things, it's nonpolar. Okay, and it is indeed nonpolar. So all you have to do is look at a molecule and look at the center atom, and if it has all the same things attached to it, it's nonpolar, like methane. Okay, methane was this. It had 4 hydrogens attached to the carbon. This is a nonpolar molecule. All right, ammonia NH3, it has hydrogens bond to the nitrogen and lone pair, so it has two different types of things. So this is a polar molecule. All right, and again, here's some example I just talked about. So this has 4 same things attached to it. This has different things, lone pairs. This carbon here has the same thing attached to it, 2 oxygens. There's no lone pairs, so it's nonpolar. This carbon has different things attached to it. It has hydrogen and oxygen, so it's polar. And this carbon here, the center atom, has 2 different things attached to it, the nitrogen and the hydrogen. Don't let the lone pairs on the outside atoms don't count in this regard here. Okay, trick number 2. Okay, the second method, if you're only given the molecular formula, specifically organic molecule, like alkanes and other things that have lots of carbons, hydrogen, oxygens, and nitrogens. And if you take Chem 111 organic chemistry, you will see this. Okay, if the ratio of carbons to oxygen is where there are more than 3 carbons per oxygen, the molecule is probably nonpolar. For example, glucose. So look at the ratio here. There's 6 carbons to 6 oxygen. The ratio is 1 to 1. This is less than 3 to 1. So this is going to be a polar molecule. So the ratio has to be greater. It has to be 3 carbons to 1 oxygen to be nonpolar. All right. Now if we look at this guy here, this is a fat. Has 18 carbons to 2 oxygen, which is a 9 to 1 ratio, which is greater than 3 to 0. So this molecule is nonpolar. So that's just a quick way to figure out if a molecule is nonpolar or polar. Okay, guess what? I think that's it for your class. Now, I could do things called molecular orbitals. I'm going to pass on that. I may give you a link to take a look at it to just to get an idea behind it. You probably won't need it if you go into organic chemistry or if you go into Chem 122. The places where you would use that would probably be in if you got into quantum chemistry. But it's just a further explanation, expanding orbital energy diagrams into molecular bonding, sort of like hybrids, but a little bit more specific. So, all right, let me just, so that this ends 121 basically. I don't know where you're going with this, but if you decide to take 122, 122 will take what we just finished, we talked about polar and nonpolar, and apply that to molecular interactions. Okay, because molecular interactions forming solids and liquids and so forth can be explained in terms of the polarity and nonpolar aspects of molecules. Also, in 122, we'll go. You just talk about acids and bases, and we sort of relate. We talked about acids and bases already a little bit in this class. If you go back, you'll see that I defined acid as a molecule giving off H plus when in water when it does the chemical reaction. Also, Chem 122 will deal more with physical sort of aspects of chemistry, like how fast chemical reactions go and how to determine, that's called rates, and an equilibrium. And whenever we draw a chemical reaction, we look like it always goes to completion, but in reality that's not the case. And we would look at things called, we look more into specific energies, thermodynamics like entropy and free energy, and even some electrical chemistry. So in some ways it's more interesting in a sense because it's more applicable to what actually is how chemistry is used in the real world. Okay, so unless I have something else as far as PowerPoints, that's about it. Again, there'll be the quizzes and homework and all that deals with this. Okay, enjoy.